All right, in lesson 2, we're going to continue to talk about expressions and variables and putting these expressions into an equation form that we can use to help us solve some problems, some algebraic type of problems and general problems. So at the end of the lesson today, we want to be able to tell which quantities in a situation can vary and which ones cannot, and also use letters and numbers to write equations representing the relationships in a situation. Before we do that, let's just make sure that we are able to calculate a percent, because a percent is going to come up a little bit later, and we're going to need to make sure we can do that. So it says evaluate and solve mentally, record your answer, and the thought process below. So we're going to talk about how to do this mathematically, but also we're going to think about just a percent. Now, when I'm doing a percent mentally, I'm often breaking it down into 10% and then doing some conversion from there. Because when we have 10%, it really is a matter of just taking a number and moving the decimal point over one place. So if I want to get 10% of, say, 300, imagine there's a decimal point here, that's going to be just 30 if I move the decimal point over one place from the 300. So if I have a bill at the restaurant and it is, say, $75.36. All right, if I'm going to figure out how much money to leave for a tip, maybe I'm going to figure out 10% first by moving the decimal point over one spot. So that's approximately $7.54. 7.536 if we're rounding to the nearest cent. And then if it's a restaurant, maybe I'll double that for a 20% tip, or I'll kind of figure out what a 15% tip would be. So when we are figuring out a percent, we are really dividing by 100. So when you have 25% of something, you are thinking, okay, well, that's 25 out of 100, 25 100ths of 200. So 25 100ths is the same as the decimal 0.25, which is also read 25 hundredths. And if you're going to calculate a percent of something, that means that really you're multiplying that fraction or that decimal times that number. So you can either multiply 25 hundredths times 200 or just 0.25 times 200. Now, maybe some of you guys are looking at this and saying, okay, well, I know 25% is 1/4. That's fantastic. Yes, exactly. What's 1/4 of 200? 50. So 0.25 times 200 is 50. So if we're going to do 12% of 200, again, think of that as 12% is 12 out of 100, and that's the decimal point 0.12, or the decimal 0.12, which is also read 12 hundredths. So 0.12 times 200 will give us 12% of 200. And when we do that, we get 24. All right. Let's do the next one. 8% of 200. So 8% is 8 100ths. And that as a decimal, 8 100ths is 0.08. So 0.08 times 200. And that is 16. So if you have any percent, let's just say p percent, really what we're doing is taking whatever that number is out of 100. So p percent of 200 would simply be p over 100 times 200. And that would give us our number. All right, when we take p divided by 100, we would get a decimal, whatever that hundredth would be. But what we're doing is we're taking that fraction out of 100 and multiplying it times the number. So when you see of, that word really means multiply. Okay, so we'll consider that as we go through some of the problems a little bit later on. So let's look at a different situation now. Now we're going to look at a situation and see if we can recognize a pattern. So we're going to be using some variables here and seeing if we can come up with an equation. But first we're going to see if we can notice a pattern. So these are what we call Platonic solids. You probably will talk about those a little bit in geometry. Essentially, it is a solid shape that has all regular polygon sides that are congruent to each other. And regular polygons are polygons that have all equal sides and all equal angles. The most famous of our regular polygons is just a square, all equal sides and all 90-degree angles. But there are other regular polygons, like an equilateral triangle. And so each one of these Platonic solids has regular polygons for its sides that are all congruent to each other. So all its sides are congruent. So the first one's called a tetrahedron. Tetra, if you know the game Tetris, means 4. It's a prefix. Now I'm forgetting if it's a Greek or a Latin prefix, but it means 4. All right. Hexa means 6. So your classic cube or dice has 6 sides, right? So hexa means 6. Dodecagon. Dodeca means 12, so that's 12 faces. And octa means 8. So 8 faces. Hedron basically means faces or sides. So 4 sides, 6 sides, 12 sides, 8 sides. All right. So here we have some characteristics. So faces or sides. So when I say sides, sometimes that's what I mean. So it's the faces. Vertices would be a point. So when we say the word vertex or vertices, by the way, vertex is the singular for vertices being plural. And then edge are essentially the lines on our different polyhedrons. So if you look at the tetrahedron up here, it has 4 faces. So 1, 2, back 1, 3, and the one on the bottom is 4. All right, how many vertices does it have? Vertices are the points, so 1, 2, 3, 4. All right, and then how many edges does it have? 1, 2, 3, 4, 5, 6. Okay, so another one that's given is a dodecahedron. We know dodecagon, again, 12, so it has 12 faces. We could number those over here. And if we counted up all of the vertices, if you went through and counted up all these vertices in the dodecahedron, you'd have 20. And if you counted up all the edges, you have 30. Okay, so that one's a little bit harder one. Let's take a look at the ones that might be a little bit easier. So a cube, how many faces does the cube have? All right, hopefully you know a classic dice, a die, has 6 sides to it, so 6 faces. How many vertices does it have? 1, 2, 3, 4, 5, 6, 7, 8. And how many edges does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, now I want you to start looking at this table here and see if you can notice a pattern as we go from faces to vertices to edges and connecting those for a particular polyhedron. All right, so the octahedron, how many faces does it have? Well, octa means 8, so we know that just based on the definition. How many vertices does it have? 1, 2, 3, 4, 5. This one only has 6. And how many edges does it have? All right, if you count up all the edges, you should have, counting them up, also 12. Interesting. Okay. So it's almost like the cube and octahedron kind of have some similarities to them, don't they? So there are some relationships between the number of faces, the number of vertices, and the number of edges. Have you noticed any? Hopefully you have. Notice that the edges, I'm going to abbreviate that E, are greater, there's a greater number of edges than faces. And there's also a greater number of edges than vertices. So edges is greater than faces, and edges is greater than vertices. So the number of edges is greater than both the number of faces and vertices. Okay. However, when we add together the faces and the vertices, we'll notice that actually the edges would be less than the sum of the faces plus the vertices, right? 4 plus 4 is greater than 6. 6 plus 8 is greater than 12. 12 plus 20 is greater than 30. So the edges are less than the sum of faces and vertices. All right, number 3. So there is a relationship between the number of faces, the number of vertices, and the number of edges. Besides just that one is greater than the other or some is greater, there actually is an equation. Have you noticed an equation, a relationship between faces, vertices, and edges that always works for each one of these? If so, write that equation. Can you see the relationship? There's a few different ways of expressing this, but you may have noticed that the faces plus the vertices, so the first two numbers, faces plus vertices, is equal to the number of edges plus 2. So 4 plus 4 is 8, and 6 plus 2 is 8. 6 plus 8 is 14. 12 plus 2 is 14. 12 plus 20 is 32. 30 plus 2 is 30, and so on. Another way of expressing this is that you could say faces plus vertices minus 2 is equal to the edges. So that's another way of expressing that same relationship. You can actually subtract that 2 over to the left side of that first equation, and we get that relationship. Okay, so now let's look at another type of polyhedron. This one's called an icosahedron. It also has all regular triangle faces. In fact, it has 20 of them. Icosa means 20. So it's 20 faces, and it has 12 vertices. Write your equation from number 3 to find the number of edges. Okay, well, which one would be the easier one to use here? If we're calculating the number of edges, maybe we want to use this one then. Because we can say, okay, if it has 20 faces plus 12 vertices minus 2, that equals the number of edges. So 20 plus 12 is 32, minus 2 is 30. 30 edges. What if we had used the first equation? Well, on that one, right here, we'd say, okay, well, faces plus vertices is 12, is equal to edges plus 2. So that's the same thing as saying 32 is equal to edges plus 2. Doing a little solving, just like we did the other day in our practice for the unit, we subtract 2 from both sides to undo the addition, and we get edges is equal to 30. So either way, we can come up with the equation for the number of edges, faces, and vertices and how they're connected, and solve for, in this case, the number of edges. So we used an equation with variables to represent a situation, and then we used that equation to solve for a particular variable. Our third situation today, changing speeds again a little bit here, a different type of problem, is this one related to blueberries and earnings. Write an equation to represent the situation. All right, A, blueberries are $4.99 a pound. Diego buys B pounds of blueberries and pays $14.97. Let's write an equation to represent that. All right, so we have $4.99 per pound. Notice B represents pound, and that comes out to $14.97. So 4.99 times the number of pounds will give us our total of 14.95. All right, and we could then solve that for b if we wanted to, dividing both sides by 4.99, and we would get the number of pounds. All right, let's look at the same problem with a few more variables. So blueberries are $4.99 a pound. Jada buys P pounds of blueberries and pays C dollars. All right, so we still have $4.99 per pound. In this case, P is representing pounds, and that comes out to a total of C dollars. So instead of having the total in dollars that with numbers, we're going to have a variable that represents that. So 4.99P equals C would be the equation. What if they're all variables? Blueberries are D dollars a pound. Lynn buys Q pounds of blueberries and pays T dollars. So just like the other ones, let's use the same process, but put the variables where they belong. So D dollars per pound times however many pounds, in this case Q pounds, so D times Q equals our total, which is T in this case. So all three of these equations are representing the same situation. It's just as we go through each one of those, we add one more variable into the mix and end up with an equation in part C here where they're all variables. Okay, let's take a look at D. Noah earned V dollars over the summer. Mai earned $275, which is $45 more than Noah did. So we're going to write an equation for that. Okay, so we got to think about this one for a sec. All right, Noah earned V dollars. Mai earned $275, which is $45 more than Noah. So the 275 is $45 more than Noah. So V plus 45 then would have to be equal to Mai's total, because Mai earned $45 more than Noah. All right, E. Noah earned V dollars over the summer. Mai earned M dollars, which is $45 more than Noah. Okay, so once again, we have V plus 45, but this time we don't know what Mai's total is. We just know it's $45 more than Noah. So there we have her total of M dollars. Okay, Noah earned W dollars over the summer. Mai earned X dollars, which is Y dollars more than Noah. So this is similar to the parts A, B, and C, where each part we're just adding one more variable into the mix. So in this case, actually we changed the variable for Noah, didn't we? In this case it's W dollars, so W plus Y, because Mai earned Y dollars more than Noah did, and that is a total of X dollars. So in each one of our situations, we are coming up with an equation to represent it, and sometimes you know the values of the variables, and sometimes you don't, but we can use each one of them to represent a particular situation. All right, last problem for today is back to those percents that we were talking about at the beginning of our lesson. In this case, car prices. The tax on the sale of a car in Michigan is 6%. At a dealership in Ann Arbor, which by the way is where the University of Michigan is, if that sounds familiar, the Michigan Wolverines, a car purchase also involves $120 in miscellaneous charges. There are several quantities in this situation: the original car price, the sales tax, miscellaneous charges, and the total price. Write an equation to describe the relationship between all the quantities when, first, in A, the original car price is $9,500. Okay, so whenever you buy something, unfortunately, that's not the total price, right? What we see as a sticker price, we don't necessarily pay that sticker price because sometimes there's tax added on or some other charges added onto that. And that's exactly what the situation is here. So we know we have $9,500. And then we are adding on to that a tax. The tax is 6%. So 6/100ths, remember what we talked about at the beginning, just 0.06. So it's 6/100ths of the original price. So 0.06 times 9,500 would be the tax. Plus another $120 in miscellaneous charges. When we add each one of those parts together, we will get the total price. Now, if you use your calculator and take 9,500 plus 0.06 times 9,500 for the tax plus 120, you should get $10,190. All right, what if the original car price was more? What if it was $14,699? Well, we used the same process. $14,699. The tax percent is the same, but it's 6% of a bigger number. So we know how that works with the percent. We know our tax is actually going to be more with this car because it's 6% of 14,699 is a bigger number than 6% of 9,500. But the miscellaneous charges are still the same, of 120. So if you punch that into your calculator, we get a total of $15,700.94. All right, you can kind of see where this is going with this problem, kind of like what we did in the previous problems with the blueberries. What if the original price is P? Now we can represent that 14,699 or that original price with P, but the tax is still 6%, so 0.06 times P. By the way, when you put the variable next to the number, we know they're being multiplied, so we can put that there. In fact, we don't even need to put the parentheses in here because order of operations does multiply before it adds or subtracts. We are adding the $120. And in this case, we're not going to be able to calculate the total, so we can either write total here, or you can use maybe the variable t to represent the total. That would be up to you. The last one is that we actually now know the total price. So let's put that in at the end here. Oops. So we have the total price of $22,000, $22,480. So in this case, that's all we know. And so we are going to essentially use the same equation as we did in the previous problem. We don't know the original price, so let's call that P. We do know that we're going to have to add on a 6% tax of that original price, so 0.06P. And we do know that we're going to have to add on $120 to that. Now, if you're looking at that problem, you might be able to notice that we could actually solve that problem if we wanted to, because we have some like terms that we can combine, and we have one single variable, P. We're not asked to do that here, but we could simplify this. So 1P plus 0.06P, if you combine these two like terms, we get 1.06P plus 120 is going to be equal to that $22,480. All right, so a little extension here would be to actually go through and see if you can figure out what that original price P would have to be. Think about how we would solve this equation and what we would do to both sides of the equation to eventually work ourselves back to that value of P. So number 2 asks, how would each equation you wrote change if the miscellaneous charges were $m? So if the miscellaneous charges were $m, we'd have to add in a variable, wouldn't we? So in that case, we would put m in place of the $120. So the equation might look like p plus 0.06p plus, instead of 120, m equals our total. All right. Or if you wanted to use kind of that second version of the equation, or 1.06p plus m is equal to the total of t. So that ends our lesson here. Main idea is we're just trying to, again, get used to taking a situation, writing an equation with multiple variables, and then thinking about how the numbers fit into that equation for the variables, or how the variables fit into that equation